Okay, so now we are going to see about a moving coil galvanometer. So first we will see what is galvanometer. So galvanometer is a sensitive device. So when we are measuring the values, we need to measure it very carefully. So afterwards, so we are using this galvanometer to measure what? Current, and sometimes to show the direction of current. Okay, direction of current. So we can convert this galvanometer into voltmeter or ammeter. Okay, voltmeter or ammeter. So I'll be telling the oral information. To see the calculation and to working construction everything, we need to knew about something in the previous topic. So that's not included in your syllabus, but I'll tell it once. So here I have one rectangular coil. Okay, I'll have one rectangular coil. So in this I'm passing the current in this direction. Okay, and I have placed the bar magnet or the bar magnet, okay, on the sides of the rectangular coil. So now I'm taking this as an any point like PQ or yes, anything. Okay, so this bar magnet have the field lines in this way. Okay, so when you look this rectangular coil, so this sides are parallel to the magnetic field. See, I have the bar magnet in this way, P is also like this and Q are also like this, and I have the magnetic field also like this. So this is fully parallel, so no force will be created. So no force. Okay, so when you look for this side, that P, I have the magnetic field like this. Now the PQ and the SR. So this is PQ and this is SR. So this magnetic field is perpendicular to this rectangular coil. So when it is perpendicular, okay, so there will be a force. Force is created. Okay, so this force is nothing but, so by this force the rectangular coil starts to rotate. So the rotating effect we will easily tell that is what? Torque. So torque is nothing but rotating effect. Okay, torque is nothing but a rotating effect. So now we will see the construction. Okay, we will see the construction of this galvanometer. Okay, so first look at this diagram very carefully. So this is the spring. Okay, so here I'll have one spring and here I'll have one spring. So this spring is made up of phosphorus bronze. Okay, and this spring is used to, so this spring is used to avoid the rotating effect at the maximum level. Okay, so it can avoid the rotating effect of the rectangular coil. I'll tell it later on how it works. So this is what the moving coil. So this is the moving coil, the rectangular coil, and inside that I'll have the fixed core, and here I will have the permanent magnet. Okay, I'll have the permanent magnet. So this is this rectangular diagram only I have drawn here. Okay, this rectangular diagram only I'll drawn here. So the same thing only here also happening. If I have the magnetic bar magnet, permanent magnets outside means, so at the rectangular coil, so for this side I'll have the perpendicular magnetic field lines. For this case I will be having the parallel. Okay, and here they have inserted one mirror. So when this mirror starts rotating, okay, it shows some value when I'm passing the light. When I'm passing the light to it, when the spring starts to rotate. So the spring starts to rotate means the rectangular coil starts to rotate. Okay, so here I can see the value. Okay, how means, so this light ray will reflect and it shows the value in the translucent scale. Okay, here you can measure the value. Okay, and this is the view of the, this is the top view. Okay, top view means, so when I see from the top like this, I can see the PQ here. Okay, because here I'll have the spring. Okay, so this is nothing but the rotating effect of the what, the torque. Okay, the rotating effect of the torque. So how the torque is created means, when I'm passing the magnetic field perpendicular to the rectangular coil, I'll be getting the torque here. So this, when I'm looking in a top view, so here I can see the screw. So here only I can see the PQ, but the RS will be in the downside. Okay, it will be in the down. I cannot see the RS. So I can see the PQ. So when the spring starts to rotate, okay, I can see the deflection in the scale. Okay, so this is the thing they have inserted in the galvanometer. Okay, so you will be having this construction inside the galvanometer, but outside only we are seeing the deflection. Okay, inside they have assigned and designed the galvanometer like this only. So the principle is nothing but, when a current carrying loop is placed in a uniform magnetic field, it experiences a torque. So which is nothing but, when I am passing the magnetic field perpendicular to the rectangular coil, so there I will have what, a torque. So torque is nothing but the rotating effect. Then only you can able to see the readings in the scale. Okay, so when this, without the spring, okay, without the spring, if the rectangular coil starts to rotate because of the torque force, so what will happen means, the mirror will turn fully. So the mirror will be on that side, so the light will not reflect on the mirror. So for that purpose only they have given the spring there. So it will rotate up to the maximum level. Okay, so so only they are using the spring here. Okay, so now, okay, so now, so I have told you, to avoid the full rotation only, here they have attached the spring. Okay, if you are passing the magnetic field to the rectangular coil, so you will be that galvanometer will experiences what, the rotating effect. So at that time the spring will rotate what, to the 180 degrees, so that the light will not reflect on the mirror. So for that reason only, to avoid the full reason only, we have attached the spring. Okay, so now we can tell the spring as what means, this is what, restoring couple. So restoring couple means is nothing but, the coil will compress and retain its original shape. Okay, in the rectangular coil I'll have that coil. Okay, so when it so that will compress and retain its original shape. Okay, so when it compress only, the rectangle coil can able to rotate. So you can take any spring. Okay, like spring means, when you just press it, it will compress, again it will retain to its original shape. So I can tell this rectangle coil force will be, torque is equal to BF. So BF is nothing but, I'll tell you, I'm taking this distance as L and this distance as a breadth. Okay, this is length and this is breadth. Okay, so this is PQRS. Okay, so I'll be having the magnetic field will be perpendicular to this sides of the rectangle. Okay, so now the BF means is nothing but, this is breadth. So force means, so the force experienced by the rectangle coil. So I can take F is equal to, I'll have the magnetic field, current, and what, the length. Okay, so the length in the rectangle coil. So breadth means I'm taking it separately. Okay, so now I can change this equation, breadth. So what is mean by force? BIL. Okay, BIL. So I can take this B and L as an area. Okay, B and L as an area. So this B and L as an area. So torque is equal to ABI. Okay, so when I have the number of turns, number of rectangle coil, okay, number of turns in the rectangle coil means, so I can change this equation into NABI. So in terms, number of turns. terms of number of turns in rectangle coil. Okay, so I can write this equation like this. So now we'll see the torque in, so first we have seen torque in the rectangle coil. Okay, this is torque in rectangle coil. So now we'll see torque on spring. Okay, torque on spring. So which means you can tell the spring as a restoring couple. Okay. So for this I am taking the equation torque is equal to K theta. So first we will see what is K. So K means is nothing but the capacity of the spring, the capacity of the spring. So how it compress, how it retain its original shape, and how it's providing the rotating effect to the rectangle coil. So this is capacity, or I can tell this is as a torsional constant. Okay, torsional constant. Okay, so then what is meant by this theta means it's nothing but twisting effect. So twist of the spring. Okay, so twist of the spring means the displacement. Twisting displacement of spring. So twisting displacement of spring means, so at what level the spring is being twisted. Okay, what is the maximum capacity of the spring? So that is called theta. Okay, so the spring compress only to the particular stage. Okay, afterwards it will not compress. So because of that reason only they have inserted the spring there. Okay, so now if the both torque are equal, I can write this equation NABI. Okay, both equal. NABI is equal to K theta. NABI is equal to K theta. So now I can change this equation. K theta is divided by NAB. Okay, so now I can write this galvanometer K N A B. I am taking this term as G. So I is equal to G theta. So what is mean by theta means is nothing but galvanometer constant. And this theta will be what? Twisting, turning effect. Okay, so this is what they have given in the working. So construction I have explained you by showing the diagram in that they have given in the book. So principle is nothing but, so how the rectangle coil is experiencing the torque. Okay, when you are passing the uniform magnetic field. So this is what the moving coil galvanometer. So our third lesson it's completely gets over. I'll send the numerical problem. Okay.